Hey Bulldogs, we are continuing our study of Calculus Chapter 2, Limits, and we are in Section 2.3, Calculating Limits Using Limit Laws. I'm on page 6 of your Chapter 2 notes packet, and we're going to actually skip over the bell work questions since you're not in class, and we're going to dive right into an example that is asking us to use the limit laws and the graphs of f and g to evaluate the following limits. So you have previously learned how to find limits at a point. So a left-sided limit, a right-sided limit, or a limit which is from both sides. There are now a few limit laws, and I'm just going to show you a peek at our textbook. I did not include a list of these limit laws in your notes because we'll look at them today and we'll never need them again. But some of our most basic limit laws are listed here in this box. And so this is on page 82 of your textbook if you're following along there. So if we define the limit of f of x as x approaches a, and the limit of g of x as x approaches a, and we are assuming that those exist, then if we are being asked to find the limit of f of x plus g of x, that is the same as evaluating their limits separately and adding those limit results together. Same thing is true with subtraction. If you have a subtracted expression or a difference in expressions, then you can evaluate the limits separately and evaluate their difference. If you have a constant number in front of f of x, you can pull that constant out to the front. If you have a product of two functions, the limit of the product is the product of the limits. And for the last one, if you have a limit of a quotient, it is equivalent to the quotient of the limit. So a lot of times they'll explain them using these descriptions below. The limit of a sum is the sum of the limits. The limit of a difference is the difference of the limits. I'm also going to jump over to page 83 in your textbook because they've got some other really great limits listed in here. So those were the first 5. The next one has to do with exponents. So basically, if you have a function raised to a power, you can evaluate the limit of that function first and then raise it to the power. If you have a limit of a constant c, that is equivalent to c. If you have the limit of x as x approaches a, that is equivalent to a. And I think that about covers our limits. Oh, there's a radical one as well. So the limit of the nth root of x is equivalent to the nth root of a. That actually builds off of the previous one we just talked about. And so what we're going to do is we are going to solve a few problems using those limit laws. Actually, we're only going to solve 2. The first one will be using limits off of a graph, and then the next one we will actually be evaluating algebraically. So if we look at example A, the limit as x approaches -2 of f of x plus 5g of x. So if I'm using the limit laws, the first thing I want to do is I want to separate these limits. So the limit as x approaches -2 of f of x plus the limit as x approaches -2 of 5g of x. Okay, and so what we want to do now is I'm going to go one more step, and I'm going to pull this 5 out to the front. And so what do I mean by that? I'm using one of those limit laws that we saw. So limit of f of x as x approaches -2, and that is the constant c. That limit law allows us to pull that constant out to the front. So we have plus 5 times the limit of g of x as x approaches -2. Now that I've separated these limits, I can head over to my graph here, and I can find the limit of f of x. And f of x is its own function here. So the limit as x approaches -2. So let's find where -2 is. And there is no preference or specification of from the left side or the right side. So that means we are looking from both sides. So from both the left side and the right side, this limit is approaching the value of 1. And then I'm going to carry down my 5. And now I'm going to evaluate the limit of g of x as x approaches -2. So g of x is my linear piecewise down here. So as x approaches -2, what is g approaching? Well, that would be approaching a -1. So we would have 1 minus 5, which is -4 for my final answer there. If you wanted to try one more example, actually I'm going to jump to this last one. The limit as x approaches 2 of f of x over g of x is the same as the limit of f of x as x approaches 2 divided by the limit of g of x as x approaches 2. In other words, the limit of the quotient is equivalent to the quotient of the limits. So the limit of f of x as x approaches 2. So here's 2 over here. So x, as x is 2, y is, I'm going to estimate that to be 1.5. And in the denominator, the limit of g of x as x approaches 2, well, g of x is equivalent to 0. So we actually have an undefined number, which means that this limit does not exist. All right, so now you've seen an example where we applied our limit laws, and that allowed us to separate f of x and g of x from each other because that's how the information was presented to us graphically as separate functions. All right, let's take a look at example 2. Evaluate the following limits and justify each step. Okay, so we're going to do the same thing. We're going to start by separating this into 3 separate limits. So the limit of 2x squared as x approaches 5 minus the limit of 3x as x approaches 5 plus the limit of 4 as x approaches 5. And for this first one, I'm going to pull my coefficient out to the front. That's that same limit law that we used earlier. So that would be 2 times the limit of x squared as x approaches 5. I'm going to do the same thing here. I'm going to pull that 3 out to the front. So minus 3 times the limit of x as x approaches 5, and then plus the limit of 4 as x approaches 5. And we had one other property that allowed us to take an exponent of an expression and move it outside the limit. So I'm actually just going to put this in brackets here. All right, so what we want to do is evaluate the limit of x as x approaches 5, the limit of x as x approaches 5, and the limit of 4 as x approaches 5. So one of our properties that I showed you earlier said that if we have the limit of excuse me, x as x approaches a, that is equivalent to a. So it is almost as though we are substituting a in for x. If you think visually what's happening here, this is the function x. So if that is the function x, that is the line y equals x. And if x is approaching a, what would our y value be approaching? Well, our y value on the function y equals x is the same as our x value, which is why this result is a. But the faster way of interpreting that, so that you don't have to graph the function x, is just to assume that this x is being substituted in with a. So what that allows us to do over here, I'm going to carry down this 2, and the limit of x as x approaches 5 would be 5. And then I'm going to bring down that power. Minus 3, same deal here. The limit of x as x approaches 5, I'm just going to replace that with 5. And then for the very last part, the limit of 4 as x approaches 5. So there was a property that said if you have the limit of a constant as x approaches a, it was just equivalent to that constant. And the reason for that is if you have a constant function, y equals a constant, that is a horizontal line at c in this case. And if you're looking for the limit as x approaches a, well, as x approaches a, wherever a is, your value of that function is always going to be c. But the faster way is anytime you have a limit of a constant number, the answer is just going to be that constant number. So we're ready to take this to the last step where I evaluate this, but I want to take a moment and let's notice a very important relationship here. my original function that I started with, 2x squared minus 3x plus 4, can you compare that to what we now have after breaking up our limits and evaluating our limits? It looks exactly like this line, except every single x has been replaced with a 5. In other words, it implies that if you are evaluating a limit, you can just substitute in this value of 5. And that is what we call our direct substitution property. So we would have 25 times 2 is 50, minus 15 plus 4. So 50 minus 15 would be 35, plus 4 would be 39. Okay. So this direct substitution property is actually going to be our first line of defense every time we evaluate a limit. So we will always start by trying to substitute a into that function. All right. On the next page, we've actually got a summary of 5 different techniques. So I'm going to show you an example of each of these. The very first one, it's what we always try initially, which is direct substitution. So take a look at example number 3. We're finding the limit as x approaches -1. So I am literally just going to substitute -1 in here. 2 times -1 cubed minus 4 times -1 squared plus 3 times -1 minus 5. So -1 cubed is -1 times 2 is -2. -1 squared is 1 times -4 is -4 minus 3 minus 5. So that would be -14 for my answer. If you were to graph this on your calculator and observe the behavior around -1 from both the left side and the right side, our graph would be approaching -14. Number 4 is a slight variation. You won't see something like this on IB, but when we talk about the limit of a piecewise function and we're finding the limit as x approaches 1, we are looking for what happens when the graph gets closer to 1, when x gets closer to 1, but not at 1. So if you have a piecewise function, we are trained, if I wanted to find, let's say, g of 1, you would substitute 1 into the second part of the function because we use this second piece when x is equal to 1. So we'd say, okay, my answer is pi. But if we are being asked to find the limit of g of x as x approaches 1, we actually don't care what's happening at 1. We only care what's happening around 1. So you actually substitute into the x plus 1. So we would have 1 plus 1, which is 2. So I just wanted you to see a difference in evaluating a function and evaluating the limit of a function when you have a piecewise function. All right, take a look at example number 5. So I'm always going to try first to substitute my value in. So if I try to substitute a 2 in, I'm going to get 2 minus 2 is 0. 2 squared is 4 minus 4 is 0. 0 over 0 is an undefined function. So if we go back up to our list, direct substitution is not going to work. Next thing I'm going to try, factor and simplify any rational functions. And you'll notice as you go through the list, option number 2 works well with rational functions. Option number 3 works well with radical expressions. Number 4 works well when you have something to expand, and number 5 works well with complex fractions. So it's usually very obvious which of these techniques you're going to use. So what we're going to do on number 5, since I know I can't use direct substitution, but I am seeing a rational function, I am going to try to factor and cancel. And on the bottom, I can factor that as a difference of squares. And my x minus 2's are going to cancel. And what I'm left with is the limit as x approaches 2 of 1 over x plus 2. You'll remember from Algebra 2, what's really happening here is there was a hole at 2, which is why this graph didn't exist at 2. What we've just done by reducing or simplifying the expression is I have eliminated the hole. How do you eliminate a hole? You fill it. So when we cancel away that factor and we simplify it, we've actually created a function that no longer has that hole. What am I going to do from here? Guess what? We just factored and simplified. We are then going to go back and always eventually use direct substitution. So I am going to substitute 2 in here. So I have 1 over 2 plus 2, which is 1 over 4. If you were to graph this function and look for the behavior of the graph as x gets closer to 2. There wouldn't be a point at 2, but from the left and the right, our value would be approaching 1/4. All right, take a look at example number 6. So this is an example of something that I could expand out. So I'm going to try option number 4, which is expand an expression, either a square or a cube. I always continue to bring over my limit notation until that moment when I substitute in. That's when the limit notation is gone. So 5 plus h squared would leave me with 25 plus 10h plus h squared minus 25 all over h. So I have the limit as h approaches 0. Oh, by the way, I could not substitute 0 in the beginning because I would have an undefined function. I'd have a 0 in the denominator. And so what we're seeing here, the 25s are going to cancel, and I'm left with 10h plus h squared over h. And I still can't substitute 0 in, but I'm not done simplifying this. So I can either factor h out and divide by h, or I can divide both of these by h. So we would have, if I divided these both by h, 10h over h is 10, h squared over h is h. So I'm left with the limit as h approaches 0 of 10 plus h, and now I am ready to substitute a 0 in because my problem came from the h in the denominator, and what I've been able to do is eliminate h by dividing it out. So when I substitute a 0 in, I get 10 plus 0, which is 10. Just squeeze that in at the end there. All right, example number 7, we have a radical expression. So I am going to use option number 3, rationalize a numerator or denominator of a radical expression. So we're so used to rationalizing denominators, but sometimes when you have a radical in the numerator, you want to rationalize the numerator, which is what we're going to do. First thing I always try, direct substitution. Can I substitute 0 in? Nope, I'm getting a 0 on the bottom. So what I'm going to do instead is I'm going to try and eliminate the radical from the numerator. So I'm going to do that by multiplying by its conjugate. So its conjugate would be t squared, whoops, let me put that in a square root, t squared plus 9 plus 3. And I'm not allowed to multiply the top by something without multiplying the bottom by the same exact expression, because technically I'm multiplying by 1, and that is allowed. That is a legal move in mathematics. So now I'm going to expand out the top. Now you'll note I'm not touching the bottom. My goal is to eliminate the radical from the top, so I'm going to expand this out. So when I distribute, square root of t squared plus 9 times square root of t squared plus 9 leaves me with t squared plus 9. Since these are conjugates, my outer terms and my inner terms are going to cancel. And then negative 3 times 3 is negative 9. On the bottom, I'm not going to change anything. I'm just going to bring these two factors over. So I have the t squared in the front, and then I have the square root of t squared plus 9 plus 3 after it. And in the numerator, my 9 and my negative 9 are going to cancel out, and that leaves me with just a t squared on top. And on the bottom, I've got t squared times the square root of t squared plus 9 plus 3. Now, remember, the original problem we had was that when we substituted a 0, we still had a 0 in the denominator. But now my t squareds are going to cancel, leaving me with the expression, I'm going to come down here, leaving me with the expression, the limit, as t approaches 0, of 1 over the square root of t squared plus 9 plus 3. And now I've eliminated the problem that I started out with, and now I can substitute 0 in. So 1 over the square root of 0 plus 9 plus 3, which is 1 over 3 plus 3, which is 1 over 6. And you might recognize this problem. We worked that in the previous section in 2.2 when we evaluated limits on a graph using a graphing calculator, and we got 0.16 repeating. That is equivalent to 0.16 repeating. Okay, example number 8. So we've done a direct substitution question. We did a factoring and simplifying rational functions problem. We did a rationalizing a numerator problem. And remember, all of these eventually take you back to direct substitution. We did an expand an expression, also eventually took us back to direct substitution. The one last type of problem we haven't seen yet, simplifying a complex fraction. So if I try to substitute a -2, and I'd have 2 plus -2, which is 0, so that is not going to work. When you simplify a complex fraction, you've got two options. You can combine the fractions on the top so that you have a single fraction, and then you can take that top fraction and divide by the reciprocal of the bottom. That works. You can use it. It's fantastic. I like to use the method where I multiply top and bottom by the least common denominator of all of my little fractions. When I say little fractions, these little guys in here, these little denominators. So I'm going to multiply by the common denominator between these two, which is 2 times x, or 2x. And on the bottom, I'm just going to treat that like 2 plus x over 1. So I'm going to multiply top and bottom by 2x. Remember, this is a legal move in math because what's 2x divided by 2x? It's equivalent to 1. So when I distribute here, 1 over 2 times 2x, my 2's cancel and I am left with x. When I distribute here, 1 over x times 2x, my x's cancel and I'm left with 1 times 2, which is 2. In the denominator, I'm not going to distribute here. I have 2 plus x times 2x. Now you absolutely could distribute, but what I'm seeing is going to happen on the top and the bottom, I have a common factor already. So if you did distribute and you got 4x plus 2x squared, you just then have to turn around and factor and cancel. And that's okay, it's just an extra step that's not needed. So I distributed to the top because I wanted to eliminate those little fractions. I didn't on the bottom because I didn't need to eliminate any little fractions. And now I'm seeing that these x plus 2's cancel, which is going to leave us with, ooh, sorry, I forgot my little limit notation in here. Pretend like that's in there. The limit as x approaches -2 of 1 over 2x. Don't forget that when that cancels, that leaves you with a 1 on top. And now we can substitute a -2 in. 1 over 2 times -2 is 1 over -4, or -1/4. Okay. The last question we're going to take a look at is not one that we're going to work algebraically in IB because you actually don't need to, but and we won't see absolute values. But when you talk about the limit as x approaches 0 of the absolute value of x, just think about the graph of the absolute value of x. That is the easiest way to interpret this. As x approaches 0, what are we approaching from the left side and from the right side? We are approaching 0. And we're going to keep it as simple as that. So the limit of the absolute value of x is 0. If you continue on and you take AP Calc BC after this course, you will evaluate limits with absolute values in much greater detail, but we're going to bypass that this year just because we've got a lot to cover in just a semester. I'm going to skip example number 10. It's another absolute value. And example number 11 is the last one. Does the limit of f of x exist if f of x is defined as, and it's a piecewise function. So if the limit exists, what we want to do is determine if at the point where this piecewise function switches from one graph to the next, if this graph has the same limit from the left side that it has from the right side. So since the break between the two pieces of the function happens at 4, I am going to substitute 4 into both of these. Why am I doing that? Well, if I'm trying to find the limit of f of x as x approaches 4 from the right side, wouldn't that be this top piece when x is greater than 4? So to find the right side limit, I'm plugging into the top piece. So I'd have square root of 4 minus 4, which is 0. To find the limit of f of x as x approaches 4 from the left side, I'm looking for this piece of the graph because I use that piece when x is less than 4, hence from the left side. So I'm plugging 4 into my expression, 8 minus 2 times 4. That is 8 minus 8, which is 0. Since you are getting the same result when you evaluate the limit from the right side as you are from the left, this limit does in fact exist, and the limit from both sides of this function as x approaches 4 is equivalent to 0. Okay, and that is the end of our evaluating limits unit. I hope you found that helpful. Thank you so much for listening.